All right, happy to see everybody back, and let's now move on with the course. Okay, so thank you so much for the course evaluation. I'll follow up with you maybe on Wednesday a little bit more. I'm still processing what you guys kind of mentioned in the course evaluation. I do have some response. We can talk about them very briefly. We'll highlight them on Wednesday. Okay, so your programming test number 1. I already met with the TA yesterday, just talk about the grading criteria, etc. So the deadline for them to give me back the raw result will be next Monday around this time. And that hopefully will take me very briefly just to get the result process and release the grades. Okay, and then we'll talk about it. Okay, programming test 1. You can definitely see me anytime after the results are released, and we can go over your answer if you want to, but you can also look at the feedback file. I'll follow up with you about this a little bit later. And your lab number 3 is also going to be released. Let's look at the semester calendar to see where we are very quickly. Okay, so we are now basically here, right? So lab number 3 is supposed to be for these 2 weeks. I will release that around Wednesday, so you can take some time to do it. So lab number 3 is not going to be covered in your upcoming written test number 1. But you also got to make sure you do it in time, learn the stuff, and then once you see the solution, there will be some follow-up activity and exercises for you to try. But if you didn't do it, you will not be able to actually get the essence about how to do the extra exercises. And for your written test number 1, it will be next Thursday during the scheduled lab time. Okay, and then around Wednesday, or maybe Friday the latest, I'll give you guys some PDF guide and also some example question for you to try out as well. Okay, just as normal. And then for sure, I think one of the feedback you guys mentioned will be some more like a Q&A. So we can do some Zoom Q&A session for written test. We can do that. All right. I would tend to guess maybe a Sunday afternoon might work for everybody. Anyway, I'll reach out to you guys about the Q&A over Zoom. It's going to be recorded anyway. Okay, we'll talk about it. All right, guys, just for this week, it will be a little bit more exceptional. For my 2101, because I'm the coordinator, I need to be present for other sessions test. So for this week, if you want to speak to me, this might be the only time I can make it. But if you really got something urgent, please still reach out to me by email. I'll make time for you if that's really needed. Otherwise, work independently, and the normal office hour will resume from next week. But Andy will still be available over the email if you want to ask him any follow-up about the labs. You're also welcome to. All right, guys, any question about the course? Good. Let's do a quick recap from before the reading week. Okay. So I think before the reading week, we basically try to walk you through about a solution to rock, paper, scissors again. I kind of show 2 of your fellow students brilliant solutions. You can learn from them, take a look. And then also we talk about the post condition for guess all suffixes, right? So that's one of the tasks for your practice test. And then we didn't get a chance to get to the right shift, but you guys can go over the solution as well. It's very similar idea. Go over them. It's also going to be beneficial for your written test. And by the way, for written test, you don't really need to wait for me to finish the lecture. I can tell you most likely it's going to cover everything about lecture material, everything until Wednesday, which I'm going to finish. Right? So you got more than a week to get prepared for the lecture material. It doesn't hurt to get started right away. And then it will also cover lab 1 and lab 2. Of course, you wouldn't be asked to really write Pascal algorithm entirely per se, but you might be asked some conceptual question about it. Okay, I'll be more precise when I release the written test 1 guide to you. But you can definitely get started already preparing for your test. All right. All right, let me go back here. And then we got this post condition here, and then get all suffixes, right? So this is basically we have to move on about the LTL language. Okay. So today, I definitely want to finish the majority part about the syntax, so we can definitely get started with some semantics from Wednesday. So that'll be the plan. All right, so let me now just go to a new page over here, and then we're going to talk about some stuff more about the syntax, right? So today we're going to do a little bit drawing and also derivation more, and to compare them, okay? So very quick reminder about the syntax over here. Oh, you know what? I'll just show you on the slides, okay? And then we'll talk about something about precedence. Right, so slide number 10, this is really the syntax guide we're going to follow for LTL syntax. And if you guys just remember, so the first 3 over here are the base cases, which we spoke about. And the others will be recursive cases, which means the number of strings or formulas that can be generated from this particular formula will be infinite. But we just got to get some idea about how exactly to generate them. And also, given some formula, how do you determine it will satisfy this grammar? So that will be the topics for today. Right? Just remember, we got base cases and recursive cases. And you also will see that we got something called, we got temporal connectivities. Well, connectives, it simply means temporal operators. Okay, so here I'm going to talk about some operator precedence, right? That's important for us to clarify first, and then we can do exercises. We'll do lots of examples today. Okay, so let me just clarify about operator precedence. Okay, let's start with that. So operator precedence, which means in the absence of parentheses, how do you group the order of evaluation? In the absence of parentheses, like this, right? Usually you will use the parentheses to force the order of evaluation. You can still use it, but when you don't really have the parentheses, what should be the order of evaluation? What's the order of evaluation? All right, let's now talk about some very simple rules over here, which we're going to follow. So the highest precedence will be the unary LTL operator. Okay, so I'll just put some comments over here. So unary will be the top temporal operator. This will be the top. And we got three of them. We got the X operator, we got the F operator, and also G. Yeah, this one is more like a future. This is more like a global, right? But we'll explain the semantics a little bit more later. But today we focus more on the syntax. So this is so-called the next operator. This is the future, and this is a global operator, right? So whenever you see these operators being present, they should be the highest precedence to be considered first. Okay, I'll show you an example in just one moment. The next category will be slightly less tight. It's called the binary temporal operator. So we also got binary temporal operator. And we got also three operators over here. We have the U, and also we got W, and also we got R. All right, just a quick reminder. So U is the so-called until operator. W is the weak until. And R here is the release operator. Right, so far we have seen two categories, right? This one will be the tightest and less tight. And the next one will be the logical operator, which we know pretty well. Okay? And the next one will be logical operator. And within the logical operator, we know that conjunction should be the tightest. And then followed by, negation first. Negation followed by conjunction, followed by disjunction, and then implication. So we said that this category over here is tightest. And then gradually decreasing. Okay. Let's see one example right away. All right. So let's say we got an operator, we got some operation over here. Let's say, okay, let me just put example here. If I got something like this, I got the future operator, and then I have some formula, just say phi 1, right? Exactly what phi 1 is, we don't need to worry. I just want to explain the rule. And then we got implication over here, and also we got phi 2. All right? Of course, we're going to see way more complicated formula a little bit later today, but let's see how we interpret this. What you got to really kind of pick up yourself is, number one, we got some logical operator right here, right? This is logical, obviously. And then we got this F over here is a unary operator, unary temporal operator. And according to the rule, you can see the unary temporal operator should be the tightest. So the way for us to understand this would be, since it is the tightest, you should really go from the operator here, go all the way until the next operator. So we'll group this in the same box. So this is considered first. Okay. And then this one here is just by itself, no operator. And finally, what we got is we got the implication. Right? So this is how you can understand this particular formula. So what we're doing is, overall is an implication. The antecedent is the future operator applied to phi 1. And the consequence is simply phi 2. All right? And you got to watch out here. Because if you look at this formula here, and then I'll say versus another one. Right? If I try to use the parentheses to really force the order of evaluation, I can do something like, I can say parenthesis, the future operator, and then phi 1 implies phi 2. Right? You can see, think about this is like a one string. This is another string. The only difference between these two strings are the opening parenthesis and the closing parenthesis. But they have different meanings. This one is saying you're actually going to, oh, sorry. What I meant to say was, beg your pardon. Let me say another verses. Okay, let me just say one more. There we go. Okay, that'll be complete. So think about this is number 1. And this is number 2, and this is number 3, all right? I think that's what I meant to say, okay? If you think about number 1 and number 2, number 1 has no parentheses. Number 2 does have the parentheses, but it will just mean the same thing as number 1, because the future operator is going to be applied to phi 1 first, and then the implication. But in version number 3, we force the parentheses right here, meaning that we're going to evaluate the implication first before we apply the future operator. Right? So if you compare 1, 2, and 3, the operator precedence will be very important when you have no parentheses present, in which case you got to determine. Okay? But when you have them, you also got to decide which way should go. All right? So in this case, I would say number 1 is equivalent to number 2. They have the same meaning. On the other hand, number 2 and number 3, they are not the same. Not the same meaning. And we'll also say not semantically equivalent. Oh, sorry, let me just write. Okay, let me just write a little bit better. It is not semantically equivalent. All right, any questions so far? Yeah, so the main takeaway from this page over here is really about the precedence for the operator, and we'll keep applying these exercises. So maybe before Wednesday, you want to make sure you have very good understanding in your mind. We always got this category the tightest, and then gradually we get to the next one, binary, temporal operators, and then the logical operator. Always keep that in mind. Okay, we're going to reinforce that by doing exercises. Okay. And before we get back to the grammar, I just want to mention some syntax issue here, which we'll run into for your lab number 3. Okay. So here, let me say this. We got something you got to write on the paper. I'll just say letter. Some comparison here. And also we got some symbol. All right. So these two are both acceptable, right? So usually when you say X, that's a letter version of the next operator. And also the symbol, sometimes you will also see in the literature, they simply put just a circle, right? Just like that, okay? You can use either way, let's say in the final exam, okay? And then for letter, for the future operator, it will just be F. On the other hand, for the symbol, it's going to be a diamond, all right? And then finally, letter here, so let's say the global operator, that one bear there will just be a square. Okay, like a square right here. So for example, let's say if I got some formula right here, if I say x phi, okay, that's one way to write it. It will be equivalent if you simply write it as, let's say, the circle and then phi. That's fine too, all right? But I think in the lecture, we're mainly going to use the letter version, not the symbol version. But sometimes I might use a symbol version as well. That's example number 1, and then example number 2. We can say we got some nested operators. We might say the future and then global, and then phi, right? This is a valid formula, but if you put a symbolic version, it will be equivalent to, so I can say the future will be diamond, and then the global will be square, and then that, right? So they're equivalent. Okay. It's a very quick comparison. Okay. Okay, if you're okay with it, let's now move on to the grammar. Okay. So in the slides, I'm just going to move on to this particular slides, right? And you can see on slide number 10, we just talk about the different classes of the operator precedence. Also, we'll talk about parentheses. We just did. And then there's a comparison I just made. And let's talk about some parsing, right? Of course, you're not required to take any parsing course before 4315. I just want to give you some idea, because in order to know about the syntax, you should really have some idea about parsing. So we'll just do some very light theory, and then we'll do lots of examples just to give you the intuition. Okay, let's see this. So context-free grammar is a grammar, basically recursively defined. So we got recursive cases, we got base cases, and somehow from the grammar, you will be able to derive infinite number of possible strings. And each string is basically an LTL formula that we spoke about, right? So there are different ways you can derive, which we'll show you. Right? And so here's some terminology here. I'll annotate. So usually we'd say the base cases are so-called the terminals or tokens. And we say the recursive case will be non-terminals or variables. Right? Let's annotate very quickly. Okay? If I go back to the grammar here, right here. So you can think about these right here. So these are the terminals or tokens. On the other hand, we got the recursive cases right here, and we call them the non-terminals or variables. All right. And then let's see what else. And we say that this phi over here, which is an LTL formula, this is a start variable. Start variable of an LTL formula. All right, that's a start variable. And then that's something I briefly mentioned last time, but when we get to semantics, you will see a little bit more. So if you look at all the temporal operator, unary one and also the binary ones. So all these, somehow when we want to define them, we will have to use the logical quantification, either universal or existential. So that's why you don't really see these quantifiers explicitly in the grammar. Okay, that's something I will also mention briefly. Okay, but we'll see the detail next time. So number one, the universal and also existential, somehow they are embedded in their definition. And if you remember, when we did a math review, whenever you talk about universal quantification, existential quantification, there's some term called universe of disclosure, like a ranges, right? So the ranges over here, I will give you some look ahead. So the ranges we are talking about here are simply just the path, okay? So the universe of disclosure will simply just be the path. And don't worry too much about it. You can simply just feel free to write it down, and we'll see exactly what I meant by path next time. But when you review later, you just remember here all these operators, when we define them, we got to quantify them over possible path. Okay. And when we get to non-terminal here, let me just say one more thing. So whenever you want to do any kind of derivation, the goal of derivation is to eliminate all the non-terminals, which we shall see very soon. If you still get at least one non-terminal in your formula, it's not really a valid formula because it's not terminating just yet. All right. And then the whole thing here, we call it a context-free grammar, the whole thing, right? So we say that's a context-free grammar. That's an acronym, but sometimes we just say G. All right. Let's also see some notation here. Okay. The way we say the set of all strings that can be derived from this grammar here, we say the language of G. Okay. So when we write something like this, L of G. L of G would be the set of strings that can be derived from the grammar G. And of course, this set here conceptually is infinite, right? It's not a finite number of string you can derive. It's infinite because it's recursive, okay? And let's see an example very quickly, okay? One example would be, let's say if I got, let's say F, the future operator, which is unary, and then I say I want to apply that into P implies Q, right? This is a valid string from the grammar. So I can say it is a member of the language of G. Simple notation, right, to understand. Now I can give one counter example here. If I got P, and think about P is like the propositional atom, right? Just some proposition, basically. Okay, it can be either true or false. Followed by F, and followed by not Q. Right? If you look at this particular string over here, okay? If you look at this one here, this alone, not G, is basically this form over here. It's fine. And when you say F applied to not G, which is also fine because F can be applied to any arbitrary formula. But now the problem is, now you got some atom over here, but I don't have any operator between these two. So that's why it's invalid. All right? So that's something you will also need to judge later after all the examples we're going to go over today. So this one here is not a valid string. You just cannot derive it from the grammar. So we say that this is not a member of L of G. Okay? Yeah, just quickly. All right, so hopefully everything's good. And then you will see on the slides, it simply it gives you a checklist about what you can do to show that a string is a valid string from the grammar. So there are three possible ways to show it. We're going to go over them one by one. I got lots of examples there on the iPad notes, the template. I'm going to do one or two examples with you in the class. The other ones you can do as exercises. I also post the solution a little bit later, so you can also compare. Okay? So there are three possible ways for you to show a string is actually a valid LTL formula given the grammar G, which we have spoken about, right? Number one would be parse tree. That one is more visual, which we're going to see exactly how to draw the parse tree. And then the second way will be something called leftmost derivation, which we did very briefly before the reading week. But I'm going to redo it since it's been a while. Right? And the third way is about something called rightmost derivation. Right? We got leftmost and also rightmost. So you ought to know the difference between them and also understand right at the front. There is not a particular way that's going to be more powerful than all the other two. Not really. So they are equally powerful. Right? You can show either way. So the bottom line, either you try to draw a parse tree, or you try to do leftmost derivation, or you try to do rightmost derivation. They're all legitimate ways to show that your string is a valid formula according to the grammar. Okay, we're going to go over one by one. Let's start with the parse tree. Okay, so here is the principle right here, and then we'll do example. Okay, well, you guys know what a tree is, right? From 2101 or 2011, the data structure. So we got something called internal nodes, which means they are the non-terminating case, like a recursive case. They will correspond to the non-terminal, right? And then we also got external nodes, which will be the leaves at the bottom level. They are terminating, basically. Make sure the tree somehow will not just grow infinitely. And they are the actual, like an atom or something that's not going to be derived any further, right? So these two are the principle. But let's go over example. Then you'll be very clear to you. All right, example number 1. Okay, we're going to do 2 of them, right? Let's do the first one in very much detail, and then I'm going to definitely do it together with you. And then the second one, you guys can try for a few minutes, and we'll check your answer. Okay. All right, let's say this. Right? You can see there's no parenthesis. All right. You can see we got some future operator, we got some global operator, and also we got conjunction implication, and also we got an until operator, right? Somehow get a mix of different operators. And we want to draw the corresponding parse tree for that. Okay, before we dive any further, whenever you're seeing this kind of question here, the principle is before you start considering this grammar over here, first consider the operator precedence, which I mentioned in the very beginning, right? Let me write it down. That's something you always got to remember, okay? So I'll put here. So before considering the grammar, the context-free grammar, first use the operator precedence to group the terms. Right? So that's the principle we're going to apply for every example. Okay? And let me just remind you very quickly about operator precedence, which we spoke about just a few minutes ago. But you're still learning, so let's get some reminder. Briefly speaking, we got, first of all, the unary temporal operator, followed by the binary one, temporal operator, and followed by the logical operator. Right? So that's conceptually what you can remember about how the order. Okay. First of all, do we have any unary temporal operator? We do, right? You can see F here and G here. So they are both temporal operator. So what you should do is you should group them first because they bind the tightest. So what I would do is, first of all, I'm going to just bind these two. All right, because here you can see F here is the tightest one, so I'll bind the next one, atom, until right before the next operator, right? So this will be the box, right? Start with the operator itself until the next operator, okay, right here. And we do something similar for the global operator, right here. So these two are the unary operators, temporal operators. And the next category would be the binary temporal operator, and which we have one. You can see this will be the one. So that means you have to go to its left and go to its right. And to its left, we should stop right here because that's another operator which we shouldn't really include, right? So the box is going to look like this, right here, all right? So that's a binary operator. So these are all the temporal operators. And then for the logical operator, you can see we got conjunction, we got implication. And we know that conjunction should bind tighter than implication, right? So the way to treat it would be conjunction over here should really bind itself first. That means this whole thing over here, the pink box, will be the antecedents. And this orange, kind of orange box here is the consequence for the implication, right? And overall, it is an implication overall, the red. So this would be the kind of a pre-processing job you have to do on the paper, on the sketch, before you can draw the parse tree. To be very, very strictly, very precise, in reality, when you define your grammar, there is a way to write a grammar in such a way that we can embed the operator precedence, but we don't need to worry. That one is going to make the grammar much more complicated, which we don't have to bother. Okay? For this course, always remember to apply the precedence rule and then use the grammar. Okay? Let's now try to see how we can go about it. Okay? Because we know overall it's actually an implication, right? We start with the outermost box, right? It's going to be an implication, basically. So we start with the 5, which will be the start symbol, start variable. Start with it, and then we do have a rule here for implication. So you can think about that one there has 3 branches. It's a general tree, basically, right? It's going to be phi, and also implication, and also phi. And one thing to note, you can see obviously, this guy over here is already, it's actually an internal node. And operator itself is actually an external node. It's already terminating. So we cannot derive any more subtree underneath the operator. That's it, right? It's terminating, okay? So this is external node. All right, good. So overall, you can see this will be the root over here. And then you can now imagine that this guy here will be the antecedents that we're going to derive into. And this guy here is going to be the consequence we're going to derive into. All right? Let's do this one here. This one is a bit easier. Okay? So this one here is going to be some unary, until operator, which you can see is right here. I'm going to, right here. Right? So that means this guy here can be further derived into some phi until phi. Okay? This one is already a leaf, but these two are still internal nodes. What should we do? Well, we should really say P and R, right? So we do have the atoms over here. So one thing very important for you to also see here. So the P here is not really a keyword. So P here, just one example. For propositional atom, it could be any expression that's going to give you either true or false, right? It can be also variable. So the P here is not really a keyword. That should be spelled verbatim. Can be something like, it can be P, can be Q, can be R. You might have a variable called C, and you say C larger than 0, right? Different example here. Just in the grammar, we didn't try to make it too complicated. So, all right, so now we can now talk about the atom here. So we got P here, and also we got R here, right? So they are simply corresponding to this. So this one here can be P, and this one here can be R. All right. Let's now finish this antecedent part. You can see this tree over here corresponds to the consequence. So let me just do a little bit more. Okay, sorry. There we go. So think about this part over here is the subtree for the consequence. Okay, let me draw a little bit better. Okay, slightly better. Okay, so think about this is the subtree that corresponds to P until R. And I can imagine that we're going to derive this subtree that's going to correspond to the antecedents right here. That one there should be, first of all, a conjunction, right? The conjunction, we can see that it's basically right here, okay? So I'm going to use the pink conjunction, okay? So that one there is going to be a conjunction, phi, okay? And then individually, the left conjunct is going to be a future operator, and the right conjunct is going to be a global operator, right? So you can see the future operator and the global operator. I can just apply. So I got future operator, and then I got global operator. So I still got these two non-terminals. I gotta finish them. So one is P and the other one is Q, right? So one will be P and the other one will be Q. All right, so if you look at this subtree right here, this one is the left-hand side of the implication right here, right? So the important thing about the parse tree is you have to make sure you can really see the corresponding part in the subtree that correspond to the formula, which we call the subformula, which I'll give you more exercise. So think about this is a subformula, which correspond to this particular subtree, all right? Guys, any question about this example here? Let me recap. Whenever you're going to draw a subtree, whenever you want to draw a parse tree for a formula which you believe is actually a valid formula. If the formula is not even valid, there's no way you can draw the parse tree, right? So think about drawing the parse tree is one way to prove that the string you're given is a member of the language, of the grammar. So step number one, you have to make sure you try to do kind of the boxing, what I'm doing here, according to the operator precedence. After that, you can now start drawing top-down the tree, right? We're doing top-down. Okay, the tree here is top-down. Parse tree. All right, if no further question, I would suggest I'll give you guys maybe some opportunity to give a try. You know, it's okay to be getting a little bit stuck in the beginning, but let's now look at this one here. All right. Why don't you guys take a look at this one here and then spend maybe 3 minutes and then see what parse tree you can have. All right, and then we'll go over the answer together. Yeah, 3 minutes. Again, step number one, you want to use the operator precedence to really group the different terms, and from there you will be able to draw the tree top down. If you don't mind, I would say after 1 minute, I'll show you what's the result for step number one. So that might help you a bit, okay? I'll give you a minute to think about how you can apply the operator precedence first. Okay, one moment, and then I'll tell you the answer for operator precedence analysis. Okay, I would say that's the most critical step. Once you get a step right, you'll be quite straightforward to draw the tree. You just need more practices. Okay. Okay, let's now take a look at just step number one. Okay, first of all, identify the atoms. We got P here, we got Q here, we got P here, we got R here. Right? And then let's see the operator, temporal operator. Let me just be consistent with my color. So that'll be, okay, pink. Sorry, not pink, purple. This is a unary temporal operator. And then we got another one here, but we got a parenthesis. Right? So that it's going to apply to everything here. And then you have the binary temporal operator, which I'm going to use. Okay, that one there. This is another one. Oh, sorry. Right here. All right, and then you also got conjunction, and also conjunction should come first. So conjunction should be right here. Okay. And then you also got implication right here, right? So implication will be basically, I'll just put a check here. So that means that should be applied before the future operator. That's more or less what you should really have, okay? Okay. Yeah, I'll give you guys maybe 1 more minute, and then we'll go over the answer together. So what I would do is, this guy here would be the implication. So after the implication, we also got the future operator. Okay, that'll be complete. The slightly more complicated aspect for this example here is we are using also parentheses to force the order of evaluation, right? That's why the boxing looks a little bit more complicated, unavoidable. Okay, just take 1 moment and then get some feel about this kind of example, but you do have a chance to do the example after class, okay? All right, let me summarize about the result from step number 1. Basically, we're going to go in the following order. We're going to go, first of all, overall, it's a future operator that should be applied to the whole thing. And then, for that whole thing there, is going to be some implication. For the implication, we're going to do, let's say, the consequence, which will be just this binary temporal operator, like before. And its antecedent is actually going to be this expression over here. And that expression just contains the conjunction, and the left conjunct will be easy, just P, atom. And the right-hand side, the right conjunct will just be some global operator applied to Q. Right? That's more or less the sequence we're going to go for the parse tree. All right, so let's now try that. Okay. So I'm going to start with the future operator because the parentheses, right? We're going to start with this. So I do have something here, right? And I have some star variable, okay? So phi, and then I got f phi. And I'm expecting that to be very right heavy, so I'm going to put it here, all right? And you can see that this is already some terminal node. This is still internal, right? And then I'm expecting the whole thing over here to be that implication symbol. And by the way, you don't really include the parentheses in the parse tree. Parentheses is only for you to see the order of evaluation, and the parse tree structure itself should already include the parentheses idea. I'll make the annotation a little bit later. All right, so overall, this phi here should be reduced to implication, right? So for implication, it's going to be here. Okay, so it's going to be basically this antecedents, the implication symbol, and also the phi consequence, right? And let's look at the consequence first, which will be right here. That's until operator. So that one there, we can see the until operator right here. And then we got the phi until phi. Okay? And finally, you can see we got a P, we got a R. So we got a P, and we got a R. So these are just atoms, right? Which we spoke about in the previous example. What about the antecedents right here? That one there is going to be overall a conjunction. So let's start with the conjunction. So conjunction is right here. So we got the phi, conjunction, and then the phi, right? The left conjunct is straightforward. It's just an atom itself. So that one can be reduced to just P. And the right conjunct here is an application of the global operator. Okay, so that one there, I'm just also going to use the purple, right? That one there is going to be G, and then phi. And that phi can also be reduced to just Q. All right, that's a parse tree. Okay, and I'd like to make 2 comments before you, if you got any question. Let me just make 2 comments quickly. Number 1, if you try to highlight all the leaves right here, F, P, like that, implication, P until R. So all these leaves together in this fashion here is exactly the formula. All right, not surprising. Okay, that's number 1. Number 2, so whenever you actually got like a subtree, so there is really some implicit parenthesis around. Okay, for example, you might be wondering, what about this particular parenthesis in the original question, right? So what I want to do, right? You can see there is some parenthesis right here, and there is another closing parenthesis right here. Okay. So the question is, where does it go in the parse tree? But it's implicit, right? So the parenthesis is somehow embedded in the parse tree. So you can think about it would be as if we got some parenthesis right here. It would be as if, right? Because we know that the future operator should be applied to the entire subtree right here. It will be as if we want to use the parentheses to force the evaluation of the whole subtree before we can apply the future operator, right? A little bit like when you guys go back to the data structure course, when we talk about like a different traversal and how you can evaluate different expressions. Similar idea, okay? But here we are still focusing more on the syntactic level. We're not talking about evaluation, which we will, starting from Wednesday. Okay. All right, any question about this? All right, not difficult, but you would just need some practice, right? So we got 2 more. So exercise for you, number 3, and also exercise over here for you. I'll give you the solution a little bit later. I'll post it on the lecture site. Practice that, and then it's going to be useful for your future test. All right, so that's approach number 1 to really show that a string is actually a valid formula in the language, which is about drawing the parse tree. Let's see approach number 2. Okay, it is something called leftmost derivation. So once we do the leftmost derivation, the rightmost derivation will be basically this, the same. It's just symmetrical. Okay, so let's see what the leftmost derivation is. Let's do that quickly, and then we'll take a short break. If you go back to the slides, let's read the definition together, and then we'll do it. Okay. Okay, what's really leftmost derivation? LMD. We're going to start with the start variable phi, like a top-down, right? Remember in the parse tree, we start with that. And you have to continue to substitute the leftmost non-terminal. So always, if there's if there are more than one non-terminals in your formula, you choose the leftmost one to substitute. So that's a principle. And that's why it's called leftmost derivation. All right? And you're going to keep doing this until there's no non-terminals remaining in your formula, and then you're done. Okay? Let's take a look. Okay, so what we'll do is, again, let's look at this example here. Before you start using the leftmost derivation to show your proof that the string over here is a member of the grammar, you still want to do the boxing, like by considering the operator precedence. Okay, for this one here, let's do it together, just for one. You can see we got the atom right here. And then as before, you can see we got this one here. And also we got this one over here. And also we got this one right here. And then we got this one here. And finally, we got this one. All right, so that's the boxing, which we did already in the previous example. Now, how does leftmost derivation work? Let's start with that. So we're going to do leftmost derivation. Okay, we basically start with the star symbol. Okay, and then if you look at this, this is how we start with. In this line here, what is the leftmost non-terminal? Phi. There's only one, right? So this is the leftmost non-terminal. All right. And then whenever we want to do derivation, there will be multiple steps. So this could be some slight confusion here, but it's not too bad. So the way to say this can be derived into the convention is to use a symbol that looks like implication. The same symbol. Okay? It's not really implication. So this one here, you can say, it really means is derived to. Okay? Okay, we start with this, and then we want to somehow derive this into something else. Which rule can we apply? Well, in this case, we can simply apply the overall is implication. So we're going to do implication right here. Okay. We're going to do implication. So overall is going to be an implication. So it's going to be phi implies phi. Are we okay with the very first step right here? All right. And then, because it's leftmost derivation, we got two non-terminals here. We got this one here, and we got this one here. And we simply want to choose the leftmost one, which is here. Right? If you choose this one here, that's wrong. It's not leftmost derivation. Okay. So we're going to choose this one here, and we know that one should be antecedents. Okay. And that one there is going to be derived into. And we know that that one is going to be a conjunction, right, overall, for the antecedents. So we're going to say here, okay, So this and this. And then implies this. Okay, let's move on. And what's the leftmost one? The leftmost symbol will now be this one here. So we're going to pick that one. And if you pick that one there, we know that it's should be derived into FP right here, right? So we're going to say this one here. And that one there is going to be apply the future operator, right? So that one there is going to be the future operator and then the phi. And phi implies phi. All right. And what's the leftmost non-terminal? Right here. That one there should be P, right? And that one there is going to be derived into, so we're going to use the P here. Okay. So it will be the F, and then we got a P here. Okay, you can see this part here is already complete. We cannot derive any further. And then we're going to have and phi implies phi. So you can see we got two more non-terminals to really finish before we complete, right? What about this one here? That will be the leftmost one. That one there should somehow be derived into this one here, right? You just gotta be a little bit more patient, right, for the complete process here. So that one there is going to be derived into, so we got F over here, and we got P, and then we got this. And we got just another global operator right here, okay? So it's going to be G, and then phi. And then we got this. Okay, right here. Okay, I'm going to continue on the left-hand side, just running out of space. I'm going to continue from here, okay? So after this, the leftmost will be this one here. So that one there will be derived into, and then we say the future operator, and then we got P, and then this. And we got a global operator. And then this one here, we're going to replace it just by another atom. So that will be Q in this case, right? Q, and then implies phi. So now we are completely done with the antecedents. What we should really continue doing is to really do the consequence, right? Let's just finish this for completeness. Now, this will be the leftmost non-terminal. So what we do is we're going to just copy that. So F, P, and then G, Q. All right, implication. And that part there should be some until operator. So we're going to do until right here. And then it's going to be phi until phi. All right, we got another two non-terminals. Choose the leftmost one. Okay, so this one should be chosen first. And that one there should be P, right? Almost done. Okay, so if you don't mind, let me just copy this part here. Save a little bit of time. Okay, right here. And this one here would just be P until the 5. Okay, we just need one more. Okay, just one more line. There we go. And this leftmost phi here can just be replaced again by R. So this is the final answer. So if you think about it, we start with the start variable phi. That's what we start with. And then we try to keep choosing the leftmost non-terminal, and eventually we get to right here. Okay, so that's how we show the proof. All right. It's a bit tedious, I agree, but it's a one way to show. Okay. Any question about this? All right, just got to make sure you know how to do it. And of course, in the exam, I could ask you maybe to try to do some derivation. That should be some easy question for you to demonstrate, which is good. In the written test, if I just want to ask you something about multiple choice, for example, I might simply say, now try to do the leftmost derivation, but I'm going to ask you what's going to be the formula or partially formula look like? Let's say this, you can think about in this way, okay? I'll make it clear. Think about this line here. This is the partially completed formula after the first derivation. So you can think about this is the first derivation, that's the second one, third, fourth, fifth, sixth, 7, 8, and 9. So we need 9 derivations in total, right? I might just say, okay, now try the leftmost derivation, and what should be the partially completed formula after step number 4, for example. Then you should choose that one. That could be one way I can ask you. You don't need to do the whole thing, but at least you need to know where to get into. Alrighty, question? Good? Okay, so let me just say something about exercise that you can try, and then after the break, we'll do some comparison about the 3 approaches. For the rightmost derivation, there's really no point to waste your time in the class. It's really just trying to do it the same way, which I can briefly mention how you can do it, but when we do the comparison, I will also highlight it. Okay, so exercise for you guys. For leftmost derivation, I got one here, right? Exercise for you. Another one here, and also another one here. All right, so we got another 3. For the rightmost derivation, if you look at the definition on the slides, right, it's basically just the same as the leftmost derivation, except you have to continue to substitute the rightmost non-terminal as opposed to leftmost non-terminal, right? That's the only thing. And for that one, you can also give it a try. Also, I'll give you the solution a little bit later. So you got 4 examples here to try, all right? Okay. All right, any question so far? We're good? Awesome. Why don't we take a short break and by taking attendance? All right, so before the break, we basically spoke about parse tree, leftmost derivation. We didn't really do rightmost derivation per se, but it's really the same principle, except you're going to choose the non-terminal rightmost as opposed to leftmost. So I want to do just one comparison of all the 3 to really, for you to get some more insights. I think that these are important insights that you really want to get when you study these 3 notions. So for parse tree, leftmost derivation, rightmost derivation, they're all legitimate and they're equivalent ways of showing that a string is really can be derivable from the grammar. So now I'm going to show you that given a particular string right here is valid, is actually in the language. First of all, I want to say that's in the language, right? L of G. Yeah, in the notes template I posted is simply blank, but I didn't really post this annotated version. So do apologize, but you can maybe just watch out to see what I'm trying to show over here. You can do the annotation later yourself, maybe after class. Right? I want to use these 3 different ways to show that the same string actually belongs to the same language. I want to draw you some connection here. Apparently, this guy here is the parse tree, right? So this one here is the parse tree. Can you guys actually see just by looking at this, is this the leftmost derivation or rightmost derivation? Leftmost. Leftmost? Can everybody see it? Okay, in case you don't see it, here's how you see it, okay? If I start with, for example, this symbol here, and then somehow I derive that, for the first step you cannot really see because that one is leftmost and rightmost at the same time. But as soon as you get to the next one, you can see to go from here to here, you can see I derive this into this one here, right? So that's the leftmost. Basically choose the leftmost and derive that into here, and etc. So when you actually look at this one here, look at always the leftmost symbol here. You can see that one is gradually derived into some string. Okay, so that's a leftmost derivation for the first one. Okay, you got 9 steps in total. So that one there is the leftmost derivation. All right, here this is a rightmost derivation, right? And let me just again highlight the non-terminals, okay, just for you to see. So start from here, and then you can see here we rightmost, right here, right here, right here, 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 and then rightmost, and that's it. Okay? Convince yourself that this one here is really the rightmost derivation, meaning that for every derivation step, you pick the rightmost non-terminal to derive further. Okay? That's a rightmost derivation. Okay? And there's one correspondence I want you guys to try to see if you can see that, right? It's a very nice way to try to connect between these three notions. That's why we said they are really equivalent ways of proving that a string is a member of the language specified by the grammar. Let's say I want to know about this particular subformula or subtree here. If you look at here, right, this is subtree. You can see for that particular one, what formula does it correspond to? It corresponds to this. Okay, I'll write it down here. So this is a subtree or subformula. I'll say a little bit more about subformula in the next page, but let's now just say subformula or subtree. We got F, and then P, and G, Q. Let's say given this particular subtree, can you kind of identify which are the steps in the leftmost derivation actually correspond to this particular subtree? Somehow this subtree can be found in certain steps in the leftmost derivation. Tell me the step number. Adrian?
1 to 6.
1 to 6, yes, okay. So, however, you want to be a little bit more careful. Because 1 here, if you think about step number 1, because I start with this, step number 1 actually also covered this as well. So you may want to say from 2 over here, okay? So let me just highlight it. So I agree with you, it should be from 2 to 6. So if you think about from 2 to 6, you basically start with this one here, and then eventually you derive that into right here. So that's the correspondence you can see, all right? So this one here corresponds to the LMD step 2 to step number 6. Right? This might be a little bit quick, but you really want to spend some time thinking about how you see that correspondence. So for step number 2, we start with this leftmost derivation symbol. Sorry, let me say it again. From step number 2, we start with this leftmost non-terminal. And then at the end of the step number 6, we derive that into this particular subtree. Okay, that's why we say that step number 2 to 6 correspond to this subtree here. Right? Think about that. What about the rightmost derivation over here? Similar idea, isn't it? All right. Any idea? What will be the step number? Give me something. It's okay to be wrong. Do you think it should still be 2 to 6? Should not be, right? Because the order of derivation is not really the same. One is leftmost, the other one is rightmost. So if you think about somehow for the leftmost derivation, it's really somehow the beginning steps. Symmetrically, for the rightmost derivation, it should be around the end. If you think about the symmetry here, right? So it turns out, you guys, I'll tell you the answer, but you can think about it. Okay? It's going to be from 5 to 9. Because, again, you kind of start with this one here. At the end of step number 9, you also got this guy here. All right? So for the rightmost derivation, it's going to be from step number 5 to step number 9. Yeah, sorry, that 9 is actually blocked from there, but it's on the notes. Okay. All right, let me recap about this page here. So for this page here, we didn't do much about derivation themselves. I assume you guys will know how to do it. right? So we got the parse tree, we got the leftmost derivation, we got the rightmost derivation for the same string, basically. And then we try to see for a particular subformula derived by a particular subtree in the parse tree, they will correspond to certain steps in the leftmost derivation and rightmost derivation. You can always find such correspondence in all the three notations. So that's why we said each notation is legitimate and equally powerful. Right? So this page here is really to carry to you that message. All right, any question about this? Yes, John.
For step 4 of the right,
Mm-hmm.
isn't that like the top of the tree, like the top of the subtree?
So you mean here, right?
Yeah.
Yeah. Step number 4, we start with the top over here. So we're saying up. So we wouldn't include step number 4 because step number 4 is actually the consequence of after going from here into here. But since we only want to see this particular subtree, so we wouldn't include step number 4. So right in the beginning of step number 4, we kind of, right in the beginning of step number 5, we kind of start with this particular symbol. And then we start from there to derive into this particular subtree. That's what we're doing. Mm-hmm. Yeah. Okay. All right, very good. If you're okay with it, I would suggest we do one more. Okay, and then we are pretty close to the end of the syntax. Just one or two more example, and then we could get to the semantics next time. Okay, let's do one more. Okay, if you go to the slides, there's one more thing I want to talk about, which is important about subformula, like a subtree. So guys, these are the exercises I mentioned. You can try to do them, right? I also kind of mentioned some possible ways I can ask you questions. Of course, there's only one possible way. Could be other possible ways too. All right, so these are some extra ones you can also try. Okay, okay, subformulas. Right, subformulas, the principle is very easy. You basically go to the parse tree, and then you want to identify how many subtrees there are in the parse tree. But there will be something you gotta kind of be cautious. You don't really simply just count the number of subtrees in the tree, because sometimes the subformula might be identical to each other. So you want to remove the duplicates. Okay, so let's do the example, and then that'll be it for today. All right, let's see how far we can get to. Let's now take a look at this. So this is a question. You're given this particular formula, and I'm already telling you that one there is valid, meaning that you can either draw a parse tree for that, or you can do the leftmost derivation, or you can do the rightmost derivation. But now the question is, I want you to enumerate all the subformulas. In that case, parse tree might be the more convenient notation for you to see, right? Not the derivation. Okay. So in order to see the subformulas, I would suggest we try to draw the parse tree. Okay, that's something we got to do. All right, and as usual, we're going to somehow use the operator precedence as the first step. Okay, so what I would do is, okay, let's draw the parse tree right away, very quickly. So this time, let me not use any coloring, right, just to make it a little bit quicker. But I'm just going to box it for you still. So we got this one here, that's the unary operator, and also we got this one here, that's obvious, right? And also we got this part here, that's a binary operator. And also we got implication right here. And also overall, we got a future operator, something like that. The first step is really there to help you, to really make sure you get the order of evaluation right. All right? So overall, it's really a future operator at the top, right? So what we do is we're just going to say phi, and then we got a future operator, and then phi, right? So this phi here should be derived into this whole thing over here. And this whole thing overall, you can see we got the, it should be a disjunction really in the middle, okay? So that one there is going to be phi or phi, all right? And then you can see the left disjunct is actually some implication, right? So for that one there, you can see it's basically some implication, phi and phi. And the antecedents is p. the consequence is just a global operator, like a unary operator, right? So G and phi. And that one there is simply just R. Okay, and the right-hand side here is going to be this whole thing, right? It's going to be until operator at the top level. Until operator, I'll try to make myself a little more space right here.
Sorry, is the feature to the left or the whole thing?
It should be to the whole thing. I think you might notice maybe the number of parentheses may not be matching, right? I agree. So I think I should fix it. But it should meant to be applied to the whole thing. Yes. Okay. So you can see here we got. Oh, actually, you're quite right. It should be, yeah, it should be the whole thing. Except that, let me just start from the beginning. Guys, I do apologize. I just got to not look at it carefully. Let me do it once more. Okay, let me do it again. Okay, good. Okay, nothing wrong with the parentheses. You can see here, the parenthesis tells you should really evaluate this first, and then that will be applied to the future operator. And then overall, it's going to be some disjunction. And then disjunction, the right disjunct will be this formula here. Okay, that would be the right way to interpret. Okay, let me do it again. Make sure that's right. So you can think about this guy here is by itself, and then the future operator is going to be applied to there, right? And this one here is going to be some until operator, and we got overall is a disjunction. That's roughly how you can understand it. Okay, let's start again. Let me at least finish the parse tree, and then I can give you a little bit idea about enumerating the sub-formula, and we'll continue from there on Wednesday. Okay, we got about 3 minutes. Okay, so overall, it's actually a disjunction, phi or phi. Okay, and then the left-hand side is going to be some future operator, and then phi, and the phi should be reduced into implication. Implication and 5, and then that will be P. And that one there is going to be G, and then phi, and then R, right? And the right-hand side of the disjunct is going to be this, which overall is going to be some until operator. So until operator, and then 5, and then P. And this one here is going to be negation. It's going to be negation Q. So if you simply highlight, you got F, P, implication G, and then R, and then disjunction, negation, and then Q, and then until, and then P. All right, so let me just make some quick notes. First of all, how many subtrees? In the parse tree. This will be back to your 2011, right? How many subtrees do we have in this particular tree? How do you figure out the number of subtrees? No, even simpler. Doesn't matter. Yeah, go ahead. You count the number of internal nodes, okay? You count the number of internal nodes. So you got 1, 2, 3, 4, 5, 6, 7, 8, and 9. There's another one, right? The G here, yeah, yes, I agree. You mean the G here? Yes, I agree. Thank you so much. That's something I missed. Beg your pardon. Thank you so much. And then that one there is going to be imply, and then G, and then okay. Yeah, we basically got 10 subtrees in total. But it turns out the number of subformulas is not exactly 10. All right, guys, we'll continue from here. But before Wednesday, it will be to your best interest to really try some exercises you will be covering in your written test. All right, thank you. We'll continue on Wednesday.